Let us do a quick recap of the division algorithm. Let a and b be integers with b is greater than 0. Um, Division by 0 is not defined. That's why it has to be greater than 0. Then there exists unique integers q and r with the property that a is equal to b into q plus r, where 0 is lesser than equal to r is lesser than b. Intuitively, we know that 0 is lesser than equal to r, or in other words, remainder, it is either equal to 0 or greater than 0, and remainder is less than b, the divisor. And we can know this by plotting it on the number line. If we plot um, the divisor and the remainder on the number line, we will see that remainder is less than b. This is our intuitive understanding, but we need the proof. Now let's go through a summary of the proof. We had gone into details in the previous videos. You can check. In this video, we are summarizing what we understood in the earlier videos. Now, let us start with the proof. We begin with the existence portion of the theorem. Consider the set S is equal to A minus B into K, such that K is an integer and A minus B into K is greater than equal to 0. So what we are saying here is that remainder, it has to be greater than equal to 0. If 0 belongs to S, then B divides A, and we may obtain the desired result with Q is equal to A by B. A is the dividend, B is the divisor, and R is equal to 0. Um, 0, if we have to assume that 0, it belongs to the set S. If 0 belongs to S, if 0 belongs to S, then B divides A, and we may obtain the desired result with Q is equal to A by B and R is equal to 0. Now assume 0 does not belong to S. Since S is non-empty, if A is greater than 0, A minus B into 0 belongs to S. Now, why we assumed k is equal to 0? Because the set value, it has to be greater than 0. You can work it out. If a is lesser than 0, a minus b into brackets 2a is equal to a into brackets 1 minus 2b belongs to S. Why we assume the value of k equal to 2 into a, the dividend, because the set value, it has to be greater than 0. Please work it out on your own. You can see for yourself how it works. A is not equal to 0 since 0 does not belong to S. We may apply the well ordering principle to conclude that S has the smallest member, say R is equal to A minus B into Q. Then A is equal to B into Q plus R, and R is greater than equal to 0. So all that remains to be proved is that R is less than B. If R is greater than equal to B, we proceed with the opposite. Um, so this is the opposite. If R is greater than equal to B, then A minus B brackets Q plus 1 is equal to A minus BQ minus B is equal to R minus B is greater than equal to 0. Um, so how do we prove that R is less than B? If R is greater than B, the opposite case, then uh, let us bring b to the left hand side. R minus b is greater than equal to 0. Then we substitute the value of r, a minus b into q minus b, and then we uh, get the quotient a minus b into brackets q plus 1, so that a minus b into brackets q plus 1 belongs to S, but a minus b into brackets q plus 1 is lesser than a minus b into q, and a minus b into q is the smallest member of S, so R is less than B. See how beautifully it is proved. Now, the second step is To establish the uniqueness of Q and R, let us suppose that there are integers. Let me now move to the alternative slide because that's explained better in this slide. We still have to prove that Q and R are uniquely determined. To do this, we suppose that A is equal to B into Q1 plus R1 and 0 is lesser than equal to R1 is lesser than B, and A is equal to B into Q2 plus R2 and 0 is lesser than equal to R2 is lesser than B for integers Q1, Q2, R1, R2. We must show that R1 is equal to R2 and Q1 is equal to Q2. If R1 is not equal to R2, without loss of generality, we can assume that R2 is greater than R1. Subtracting these two equations, we obtain. So what we need to do is we must show that R1 is equal to R2 and Q1 is equal to Q2. If R1 is not equal to R2, in our assumption, without loss of generality, we can assume that R2 is greater than R1. Subtracting these two equations, we obtain A minus A is equal to 0 is equal to brackets B into Q1 plus R1 minus BQ2 plus R2 is equal to B into brackets Q1 minus Q2 plus brackets R1 minus R2. So we obtain the coefficient of B. This implies that R2 minus R1 is equal to B into brackets Q1 minus Q2. We bring this expression R2 minus R1 on the left hand side. This implies that B is a divisor of R2 minus R1 by theorem 10. What is the theorem 10? If D and N are positive and D is a divisor of N, then D is lesser than equal to N comparison property. So by theorem, this comparison property, this implies that B is lesser than equal to R2 minus R1. But since 0 is lesser than equal to R1 is lesser than R2 is lesser than B, we have R2 minus R1 is less than B. How do we obtain this expression? R2 is less than B. So R2 minus R1 is also lesser than B. This contradicts B is lesser than equal to R2 minus R1. So we must conclude that R1 is equal to R2. Now from this 1.5.2, we have 0 is equal to Y0 because we have concluded that R1 is equal to R2 is equal to B into Q1 minus Q2. Since B is greater than 0, this tells us that Q1 minus Q2 is equal to 0. Because this expression evaluates to 0 and B, we know that B is the divisor, it is greater than 0. So this coefficient Q1 minus Q2, it has to be 0. That is Q1 is equal to Q2. We know this, so this is simple maths. This completes the proof of the uniqueness of R and Q in 1.5.1 here. One more thing that I wanted to go through. In this alternate slide, they had come up with the Archimedean property. You can use this, not necessary, but I only wanted to touch upon it. The set S is non-empty since by the Archimedean property there exists a natural number n such that n is greater than minus a, and so you can go through this, the Archimedean property. It simply says that there exists a natural number n such that n is greater than minus a, and so n into b is greater than equal to n is greater than minus a. I don't want to confuse you. It simply says that according to the Archimedean property, there exists a natural number n such that n into b is greater than equal to n. This is self-explanatory, and this we need to know. So do not confuse it with what we with the proof. This we only need to know. Um, Now, the proof is done. The integer q in the division algorithm is called the quotient upon dividing a by b. The integer r is called the remainder upon dividing a by b. Now, let us consider one example. For A is equal to 17 and B is equal to 5, the division algorithm gives 17 is equal to 5 into 3 plus 2. For A is equal to minus 23 and B is equal to 6, the division algorithm gives minus 23 is equal to 6 into minus 4, the value of k plus 1. There are many instances in this book where there are integers a and b, and we will want to show that a is divisible by b. In such cases, it is usually best to proceed by writing a is equal to b into q plus r, where 0 is lesser than equal to r is lesser than b, and use properties of a and b to show that r is equal to 0.